Hi, in today's video we are going to do a tutorial problem. We have started talking about introduction to reactor design, and I have discussed about the relations between concentration and conversion of various uh, I mean constituents or participating species in a reaction. Now, based on that stoichiometric understanding, I wanted to show a numerical example, and I've also received a lot of requests from you people that you would like to see some numerical problems being solved. So, this is an effort to bring that into play. So, we have a question here. I have taken this from one of the example problems in Octave Levenspiel that I referred to for in general for all the lectures. So here we have considered a feed where CA0 is of 100 units, CB0 is of 200 units, and there are also inerts CI0 of 100 units. And the type of reactor in use is a steady flow reactor. The condition of the reaction is the isothermal gas phase reaction, and this is the chemical equation. So A plus 3B gives 6R. Now it is seen that at the outlet we have Ca equals to 40 units. So now the main objective is to find what are the values of Cb, Xa and Xb at the outlet. Okay. So let's get started with this problem. So first I will make a rough sketch of this problem. Okay. So let me just draw a steady flow reactor. Let me just draw a tubular reactor over here as my steady flow reactor. So at the inlet point, we have Ca0 as 100, Cb0 as 200, and Ci0 as 100. Uh, 0, 0, yeah. So this is my inlet condition, and the reaction taking place is A plus 3B gives 6R. Now at the outlet we know Ca equals to 40. This has been told in the this question problem, example problem. So Cb, Xb and Xa, these are our objectives to find. Also we have been told that this is an isothermal gas phase reaction. So obviously, when we have an isothermal gas phase reaction, that means isothermal means T being constant, but there will be a concept of volume ratio coming in because we have gas phase reaction. Okay, this is the first identification that we need to do. Concept of volume ratio will come here. Okay, so let's start the calculations. So we are going to find epsilon A and epsilon B first. Let me write this clearly. The volume ratio is signified as epsilon with the subscript related to the participating species. So epsilon A and epsilon B we are going to find first. For that we are going to choose on the basis of our one of the constituents. So I am choosing A. Okay, on the basis of A I am going to calculate. So at the inlet point where Xa equals to 0, that is the conversion of A is 0, there has been no reaction. The total volume is 100 units of A, let me write 100 A, plus 200 units of B, plus 100 units of I inerts. So in total you have 400 volume units. At the outlet, or let's say when Xa is fully converted, I cannot say this as the outlet point because we see at the outlet we have Ca equals to 40. So obviously this has not led to 100% conversion. But for the formulation of volume ratio, you are well aware that you need V at Xa equals to 1 minus V at Xa equals to 0 by V at Xa equals to 0. This will give you the volume ratio for A. So at Xa equals to 1, if all of the A is consumed, that means 0 A, then how much B will be consumed? For 100 A, you need 200 B. So if you have no, for 100A, you need 300B and you only have 200B in the system. Then obviously you need another minus 100B over here to show that for every 100A, there is a consumption of 300B, obeying the chemical equations stoichiometry. Okay, and you will get 600 R as your reactant product side material. Also, this inert will pass out completely unreacted. So 100 I will be there, right? Therefore, this overall quantity now becomes 600 volume units. I hope this is clear. Now we are simply going to find this ratio. So epsilon A becomes 600 minus 400 by 400, which is equivalent to 0.5. Okay. Now for finding epsilon B, we are going to use the formulations for special case 2. So in special case 2, what we had was batch and flow systems of gases of changing density but with constant temperature and constant total pressure. So you can refer to the previous lecture for this equations. I'm just directly writing the equation over here. Epsilon B equals to epsilon A Cb0 by B Ca0. This small b over here is the stoichiometric coefficient of the reacting species B. So if you plug in all the values over here, so epsilon A was 0.5, Cb0 was 200, small b was 3, if I'm not wrong. Yeah, this is small b, this is equal to 3 multiplied by Ca0. Ca0 was 100. So this becomes 1/3, right? Now once you have this, you can now find Xa, Xb and Cb easily. So Xa for a gas phase isothermal reaction will be given as Ca0 minus Ca by Ca0 plus epsilon A Ca, and this will give you 100 minus Ca was 40 at the outlet, so we are going to use that value, by 100 plus zero point 0.5 into 40. This gives us 60 by 120, that is again 0.5. So A has 50% conversion. Now coming to B, so XB, let's find out what is XB. The formulation is BCA0XA by CB0. So if you plug in the values, small b was 3, Ca0 was 100, Xa we have just found as 0.5 divided by Cb0, which is 200. Then we'll get 0.75. Okay, so B undergoes 75% conversion. Now coming to finding the exact Cb value, that is the outlet concentration of B. So Cb equals to Cb0 multiplied by 1 minus Xb by 1 plus epsilon B Xb. If you plug in the values, so Cb0 was 200 multiplied by 1 minus Xb, which we have just found, 0.75, divided by 1 plus epsilon b we have found as 1/3, multiplied by Xb, which is again 0.75. This gives us Cb value of 40 units. So this is how we have found for the isothermal gas phase what are the values of XA, XB and CV for our problem statement. That is it. Thank you.